Today we're going to talk about Gaussian processes, and as it is the traditions of this class, the first thing I'm going to write on the board is the thing I always write on the board, which is that if your data y are drawn, if you have data y and they are Gaussian distributed, so there's the data are predicted by some model, but then there's Gaussian noise, then the log of this is -1/2 y minus m transpose c inverse y minus m. That's chi-squared. This is -1/2 chi-squared is the log of the probability of the data given the model. Ring a bell? It's been on the board at least half of all classes. Now we are going to have to complete this. This isn't enough. We actually need the term here, which is 1/2 the log of the determinant of c, and actually technically it's 2 pi c. That expression is exact for the Gaussian. So if you know that you have data, if you know that the difference between your data and your model, there's a lot of assumptions. Remember in the first day we went through all the assumptions underlying this, is a boatload of assumptions. But roughly speaking, this is the probability of the data given the model if the difference between the data and the model is Gaussian distributed with a covariance matrix correctly described by C. And it has 0, mean, etc. There's various things. There's a million assumptions. We talked about those assumptions. But anyway, this is the Gaussian. And all I've done is add this additional term, which is part of the log of the Gaussian, because the log of the Gaussian is the exponential of this times a normalization factor, which is this. And we need this because we're going to start doing inference here. I said in the description of this week's class, we're going to start by thinking of the Gaussian process as a noise model. If we're modifying the noise, then we're modifying C. That means we're modifying this term too, and we have to pay attention to it. Sometimes you see, well, anyway, I don't want to talk about it too much. By the way, this is the determinant of a matrix. There's many things to say about this term. One thing to say about this term is there's a lot of fast linear algebra here. People work on fast methods in linear algebra, and I think I won't talk about it so much this Gaussian process class, but I might talk about it a little bit next Gaussian process class, how you do this fast. But one of the interesting things is people know how to do this term fast, but almost nobody can do this term fast. And in fact, if you ask linear algebra people, like people at Courant, I need this to be fast and I need this to be fast, they're like, no, you don't need to know the determinant. And then I'm like, yes, I do. And they're like, no, you don't. You go back and forth. And finally you say, look, here's my probability expression. And they're like, oh, no, you need to know the determinant. And then they're like, you're done. Like, we can't help you. There's almost no work on making determinants fast. It's like a really very unexplored area. There is work on it, but it's not nearly like there's been work on this term. And one of the reasons for that is most people who use Gaussian processes are really using them as like function interpolators and things, and they only need this term. But we are going to want to put probabilities on things, so we need this term as well. And that'll come up as we go. But anyway, just a side note. And by the way, getting a determinant is as hard as inverting a matrix. So it's as computationally as expensive as inversion or factorization. So if you factorize this matrix, if you factorize it into eigenvalues and eigenvectors, you can, from that factorization, get the determinant and get its inverse. So that's kind of the reason that everything is equal complexity. Inverting, solving, and determinant taking it are all same complexity. And I've said things before which is that you should actually never take the inverse of a matrix. You should always use the solve operator. And you should never take the determinant. You should take the log of the determinant. And there's various things I've said before, and hopefully I'll say them again next class. Because I'll get more practical next class. This class is more like, what's the theory of Gaussian process? And next class hopefully will be like, how do you actually do this in practice?
And when you say you should not, is it like just a computational consideration?
Just computational.
Or stability? Okay.
Yeah, it's computational, like numerical stability. Yeah. It's not really speed, it's numerical stability. Because the thing that you want to know is not this inverse. You want to know this scalar product. So you should be using something that gives you this scalar product accurately, not the thing that gives that inverse product. That's what it relates to. And similarly, in the determinant the determinant is the product of the eigenvalues. The eigenvalues generally have a huge range, so you don't want to be producting numbers that have a huge range. You want to be adding them in the log. That's why you want to get the log determinant, not the determinant. So it's funny that the thing that comes in here is the log determinant, which is the thing that is actually numerically stable. So that's interesting.
So you're saying adding is always cheaper than multiplying?
No, more, it's safer.
Oh,
It's numerically safer. Actually, it's also been faster until recently. There was a Quanta article that now multiplication is as fast as addition. I don't know if you saw that.
Oh, the new way of multiplying.
Yeah.
It's
It's
amazing.
really cool. It's so cool. There's such a good. By the way, Quantum Magazine, which this is a plug for the Simons Foundation, but Quantum Magazine has really good math coverage. And the recent article, which is like the best, like they've just discovered linear time multiplication. So multiplication is naively n squared because you have to multiply every digit of one number against every digit of the other. But it turns out they've just found the linear time transformation. People knew there would be a linear time algorithm, but they just found it, like last year or something. I mean, it's crazy.
so it is now in the, well, I guess it comes in the, it's processed, it's
It will
on the
not
right?
hit processors for ages, and it may never hit processors because you only fold over to improving at billions of digits.
Yeah.
Or millions of digits. It's only better at millions or billions of digits, so. Incredible though, incredible. And the story about it is really good, and it gives you a sense of how it works. It's very neat. Good. Good. What's next? Okay, good. So now imagine that, now I want to construct something, and I'm going to be pretty concrete here. I'm going to think about, imagine we're doing Kepler data analysis. So we have Kepler light curves, and we're looking for transiting planets. The reason I'm going to talk about that case is it's a case where people have actually used Gaussian processes a lot, and it's a case that some people in the room know, and it's a very simple one-dimensional case. Gaussian processes have very high dimensional generalizations, and I will hint at those, but most of the usage in astronomy right now is in one-dimensional problems, and one-dimensional problems are really easy to understand. So let's start with one-dimensional. So the idea is that this is going to be an n point, so this is an n vector. This is going to be an n-point light curve, you can think of it, meaning the brightness of a star at a function of time. You have the brightness of the star as a function of time. And then this is going to be a transit model. And of course, transits are multiplicative, not additive, and you can just ignore that. Let's assume it's an additive signal for now. We're being rough here. But multiplicative signals are like additive signals when they're small, and transit signals are small, so we're not that worried about it. But anyway, this is going to be a model for the data. This is going to be the data. But in addition, when you're modeling Kepler, there's also all sorts of systematic problems with Kepler. Brightnesses of stars in Kepler do very structured things because the spacecraft, which is very precise, has structured systematic issues. It has pointing, jitter, and stuff. So what people usually do is they don't do this model. Instead of having y minus m, they have y minus m minus some model for the systematic problems with Kepler, which is usually done as a large linear model. And people in this room have done these models. So it's some model where it's some set of eigenlight curves, as it were. Some this is going to be a n by m matrix of eigenlight curves, and this is a set of m weights with which those eigenlight curves are added together to make a systematics model. And this is the standard thing people do in Kepler right now. Yeah.
So A only contains the systematics light curves.
Yes.
It does not contain any of this. You need to be careful that in A there's no signal there.
And that's the hope, right? Right. That's a long story. There's a long story about how you would actually construct this object, but let's imagine that we're very clever. We are very clever, and we construct this. There's a set of papers that actually probably Rodrigo has done models like this, and Foreman Mackey has done models like this and was one of the pioneers in the Kepler community on this. And yeah, it's hard to make this systematics model correctly, but let's imagine you have a model that is only capturing problems with the spacecraft. This is only capturing exoplanet things, and so if you do your inference correctly, you will learn both the systematics and the light curve and the transiting planet. And this is implicitly parametrized. So really, I should have called this m of theta. It's implicitly parametrized. But since I don't care about this part of the problem right now, I only care about this part.
The thing that makes it work is that A just depends on stuff that the spacecraft knows about.
Yes.
And not things like what's going on in the rest of the universe.
Exactly.
So
That's
you
the
don't have
idea.
to have a
If-
good.
Yeah, if we were perfect, which we're not, but if we were perfect, this would only contain properties of Kepler. So it would be like
And the time,
like
things
time,
like that.
temperature, spacecraft orientation, temperatures of different parts of the spacecraft, time since it last downloaded data, various things like that would appear here. That's one way to think about it. That's actually not how we construct it, but that's what we hope it contains. Good. And I have a whole story about how you construct those, which is a fun problem. Okay, now, imagine now what I want. This is a nuisance model. So if it's a nuisance model and I'm Bayesian, I'm going to marginalize it out. So let's do the simplest marginalization we can possibly do. The simplest marginalization we could possibly do is we believe that we know this housekeeping data about the spacecraft exactly. So this is a known thing. And this is a set of weights we don't know and we truly don't care about. So then what we will do is we will put a simple prior on the weights. And the simplest prior we could put on the weights is that it's Gaussian. So it's also Gaussian with, say, zero mean and some covariance matrix. And this covariance matrix is going to be m by m, because this, as you recall, is an m vector. This is an m vector of weights. And so we're going to put some covariance there, and we're going to assume it's Gaussian. So again, if I took the log of this, it would look just like that. It would be the log of the probability would be -1/2 W transpose lambda inverse W plus 1/2 ln 2 pi lambda. Like that. People good? That's a capital lambda, by the way, not a caret.
How do you decide the parameters of this Gaussian? Like,
Hold that thought. That is going to be, in some sense, the whole point of the next 2 lectures.
well, I'm glad I'm not-
So if you don't feel like I've answered that by the end of today's class, it's going to get ugly though, because we're about to take m to infinity. That's the weird thing. We're going to make this infinitely large in a moment, which is a little weird. But anyway, we haven't got there yet. So now imagine that I do this. This is a nice, beautiful thing because it's a Gaussian. This is a Gaussian, and so I can do marginalizations like in closed form. So I can make closed form marginalizations. So it turns out if I do this and I put on this prior, and I now compute the marginalized likelihood. So now what I want to compute is the probability of the data given the model, and then given some other things. Remember we said we know these systematics, and as you've correctly identified, we've also assumed that we have a prior on those systematics, which, you know, is a little dubious, but anyway, we'll get back to that. That you can think of as being integral of the likelihood, P of y given the model, times the prior on the weights that we don't care about, and integrate out the weights. And this is, I should have put in other things here. This is comma, A, lambda, and weights. So the prior, this is the likelihood of the data given the model, the systematics model, the prior on it, and the weights. But I can just integrate this out. Because it's a Gaussian, this integral is closed form. And I'm going to show you the form of it in a second. Now, but before I show you, I just want to give a little hint of mathematically why this is so simple. There's 2 kind of things to think about here that show that this is extremely simple. One thing is, this thing is quadratic. This is a quadratic form, and this is a quadratic form. So when you multiply together, you add to these 2 quadratic forms, and when you add quadratic forms, you get a quadratic form. And there's a mathematical operation which you learn in high school, which is called complete the squares, which you then forgot and have never used again. And now you have to do it in a vector matrix context with non-square matrices. So it hurts. But the square completes really beautifully. So that's one thing to say. It's just a complete the squares problem. The other thing to say, though, that's amusing, is that if you have 2 Gaussian numbers and you add them, the distribution of the sum is also Gaussian. If you choose Gaussian distributed numbers and you add them, the distribution of that sum is also Gaussian with the sum of the variances. So what happens is actually this variance just adds to this variance, and so the answer ends up being really trivial. So here's the answer. The answer is the log of the probability, the log of this probability, y given the model, and now we have these auxiliary things, a and lambda, is just exactly that form, -1/2 y minus n, transpose, C inverse, but now this matrix is going to be different, and I'm going to be explicit about what the C matrix is, plus 1/2 on 2IC. Now I've written that equation on the board twice. And C is going to be the original noise model we had before. What was our original noise model? I didn't say over here, but if this was old school chi-squared, this thing would just be a diagonal matrix of sigma squareds. So C has a diagonal part, which sometimes people write as sigma n squared delta n, or something like that. You know, like people sometimes write it like that. That's a bad way to write it because it's not coordinate free. But we're going to get not coordinate free totally crazy in a second, so I don't really care. So if I think about the n element of this, but whatever you want to call this thing, there's a diagonal part. And then there is, I mean, if you wanted to write this coordinate free, by the way, I don't know how much people care about coordinate freedom, but if you want to write it coordinate free, here's how you write it coordinate free. Just because it's amusing, I like this. It's the sum over data of sigma n squared, un transpose, where these are the unit vectors in the space. Is there a math physics class in the graduate? Is this form used ever? No one ever writes things like this as far as I can tell. But that is the coordinate free way to write it. There's a set of unit vectors, one for every data point. Anyway. So this is the noise model. This is like the noise model for your original data. But then we get added. What happens is when I did this integral, I have to add to the variance. I said the variance is add. This thing is n by n, right? Because there's n by n data points. I have to add in this variance lambda, which is only n by m. So of course it comes in like this. A lambda A transpose. This thing is also n by m. Because A is n by m, n by m, n by m, n by n. So this thing is n by n. So that, now I'm just asserting that, and you could prove it by doing completing the squares. So you can complete the squares and prove it. That's an exercise for the reader. Only do it if you enjoy linear algebra. But it's also kind of obvious because what I did is I added to this Gaussian. Remember, this thing is supposed to be a Gaussian. I added another Gaussian deviate to my Gaussian deviate, so the total sum has to have be Gaussian distributed. And because I'm multiplying the W's up by A, I have to take A's on both sides of the variance. So you can think about it as dimensional analysis. There's a lot of different ways to think about it. But anyway, good. Are there questions to that point? Yeah.
I don't know if you mentioned it, but the derivation is in our research note.
Oh, yeah, I forgot to say that. There's a Luger et al. RNAS that has the derivation. It's an
2017.
Is it 2017? The RNAS, if you may know, is our papers in the AAS. They're unrefereed papers in the AAS that are 2 pages. Despite the fact that it's a 2-page paper, I think we have like 3 sections and an appendix. Because I don't know how we needed that for 2 pages, but anyway. But there's a derivation of this if you want to see it.
So 2 pages include the appendix?
Yeah. Within the 2 pages, and references. Actually, the main argument people gave us on that paper is that we didn't refer to the right literature, because the literature you need to refer to is more than 2 pages. I think they shouldn't count the references against the 2 pages, but anyway.
But, you shouldn't have dismissed the linear algebra, I mean, the completing the squares. It's a very delightful
It's
thing.
beautiful.
To do
It's
it
so
for a low
beautiful.
dimension, like 2 Gaussians. It's so
It's really,
satisfying.
yeah. If you just do the one-dimensional Gaussian case, it's a really
Yeah.
beautiful thing.
Yeah, one
It's
should
true.
just do it.
No, it's fun. And it really reminds you of high school algebra, which maybe is a good feeling or a bad
And the
feeling. I don't
experience
know.
when I discovered that for myself the first time was so cool.
Yeah, it's exciting.
Wow. But then,
No,
of course, you know that if I'd been better educated, I wouldn't have had that
Well,
discovery.
one of the things that it points out, so Glennis is saying, like, it's fun to rediscover it, but one of the things it points out is that you learn high school math in this kind of decontextualized way. Like, when you learned completing the squares, you had no idea why you're learning this. And then, like, 15 years later, if you're an astrophysicist, you actually have to use it, and then you're like, oh, that's why that works. So there is kind of an issue with like the order in which we learn things.
Sorry,
Good.
so in the
Yeah.
first term of the C theory seems to assume that the original C is a diagonal matrix. But what if the original one is not a diagonal?
Good.
So
Here-
you just still sum them, or?
Yeah, good. So here I've assumed, actually the funny thing about this is I haven't assumed anything because these could be
Yeah.
arbitrary eigenvectors, and so I actually haven't assumed anything when I wrote this form. But I am implicitly saying that this is diagonal, but it wouldn't have to be. No matter what noise model you started with before, so this is a very good question. Whatever noise model you had when you started, this whole process of multiplying in this prior and integrating always just adds that term. So it's that simple. It's whatever covariance matrix you had before plus this new term. And that's like, now, that is, it's weird to say it, but that is almost all of the true content of Gaussian processes, oddly. We're now going to talk about how Gaussian processes are actually implemented, what people actually do. But a lot of the challenge of understanding them is this point, that if you are adding in some additional linear terms and they have a prior on them that's Gaussian, you can integrate it out and you just are left with this n by n object. That's all you need to know about it.
So,
That's going to be important. Yeah.
Why are they called Gaussian processes?
Why is it called a process?
Totally confusing.
Yeah, why is it
me.
called a process? It's called a process because it is going to be a function. There's going to be a way we can think about it as a function generator. And to give you a little preview of how it's a function generator, this is a function generator here. I've said that I'm adding in something which is some design matrix. This is a design matrix times weights. And those weights are Gaussian distributed. So the funny thing about this is a prior over functions in a weird way, because as I add different weights here, I get different functions.
Sure.
So it's a function generator. It's a Gaussian function generator. Now, why is it called a process? I think it's called a process for 2 reasons. One is that it's a function generator, and the other is that it is, in a certain sense, infinite dimensional. We're about to go infinite dimensional, and that means like it has non-parametric. For instance, you can't know these weights in some sense when you go infinite dimensional. Anyway, I'm not really going to answer that. There's several times I'm going to say words that I don't know why they're being used. One of them is process. In a minute, I'm going to say infinite reproducing Hilbert space. And Andy Casey promised me that he would ask me, can you say more words about that? And the thing I know about an infinite reproducing Hilbert space is that it's called an infinite reproducing Hilbert space. That's the sum total of my knowledge.
It's probably related to the multiverse.
Yeah, exactly. It is the multiverse. Yeah, good.
Isn't this whole thing also just called Kriging? Gaussian
Yes.
processes, but that's an even more useless name.
Good. There's a bunch of. Oh, by the way, yeah.
Geospatial physics, I think, or geospatial stuff. They call
Right.
it.
It's
Although-
an ancient. I mean, the idea is so elementary. It
Yeah.
must have been used for centuries.
Yes.
G-I-N-G.
Good.
I?
G-I-N-G.
Yeah.
Probably some person who used it.
Yes, it is. It's named after a person. Yeah.
Oh.
So if you're in the geophysics literature, what I'm talking about is called Kriging.
Thanks, all this time I thought it was a verb.
It was. No one knew what he was talking about, so they just, that thing.
He's Kriging.
I presume Craig is the person's name.
I think the person's name is Craig, actually,
Yeah.
so it is a verb.
Oh,
It's
okay.
like when we all speak of
I
hockey.
think it's exactly. Barking, exactly. Good.
That was a pretty good joke.
No, it was a really bad joke.
Better than I realized.
But there's another thing, but actually the kriging, so it is said that it's called kriging in geophysics, but I think it has a slightly more specific meaning, and let me point out another thing is that the mean of a Gaussian process is because it's such a simple idea, is a very old idea, and it's called a Wiener filter. So you may know that if you have sparse data and you need to predict a new data point, the minimum variance prediction of your new data point is the Wiener filter, and the Wiener filter requires that you know the covariance structure of your data. If you know the covariance structure of the data you do have and you're trying to predict a new point, the best way to predict it is a Wiener filter. That's an extremely old result. I assume it's Norbert, but I don't know which Wiener it is. But it's a very old thing. And but that's also the mean of a Gaussian process. So Gaussian processes have a really old kind of signal processing past, and Wiener filters are used all over the place because they're like Fisher optimal, they're information theory optimal filters or ways of combining data. So these are those, and I think kriging, if you go back to the old papers where it's called kriging, I think they're really Wiener filtering. They're not really doing the whole covariance structure. Okay, good. Good. So we haven't actually seen anything that anyone would call a Gaussian process yet because I'm still just talking about this generic case, or this systematics model case. But now, let me say one thing. So technically, this is a Gaussian process already, although it's not what people usually mean by a Gaussian process, because this one is non-stationary.
So what is the Gaussian process? Is it a term in that expression? Is it a sort of philosophy, or?
I don't.
I'm sorry to be so.
Yeah, let's re-ask that question when we look at, because when we look at how we predict new data, it might make more sense that it's a process. But I'm
in
not
any
sure.
event, when you use the word, you're referring to a term?
To
or
me,
the whole methodology?
To me, I'm referring to all of the methodology where you add Gaussian, where you add
noise with
Gaussian
unknown.
that is kind of a nuisance. When you add a nuisance in Gaussian form, yeah, we'll see how it becomes kind of non-parametric in a minute.
I have a question.
Yes, go ahead.
So when you talk about Gaussian process, like usually sometimes people talk about like a stochastic process, they just mean a sequence of random variables. Is that not the sense in which you're using Gaussian process here?
I don't know exactly whether, people will sometimes say, that are like the idea that a process as in it produces new variables as you go, like as you're creating new variables. So you can think of it that way as you go forward in time, the Gaussian process. But I don't know if that's why it's called a process, because that doesn't apply to like Dirichlet process or Chinese restaurant process or whatever, all the other processes that are out there. So I don't actually know what unifies all the things in the box called a process, because there's a lot of weird things called process. Maybe somebody knows. Okay, good. Point. Next point. Where are we? Okay, good. So now imagine that instead of putting, this is a design matrix, right, which is n by m. Now let's imagine instead of putting in Kepler's systematics in my design matrix, I put in something that was stationary, like something that doesn't know about time or doesn't have, that is the same at all times. There aren't that many things. One of them is sines and cosines. So instead of putting Kepler's systematics here, I could have put in sines and cosines. Because sines and cosines create a complete translation invariant basis for the line or whatever. And in fact, actually, sines and cosines taken up to a complete basis for any Euclidean space or whatever. So I could replace these with sines and cosines and put some prior on the sines and cosines. And then if you think about it, this prior on the sines and cosines would be like a power spectrum, right? Because it would be how much amplitude do I expect on sines and cosines in here. And this would be the sines and cosines. Yeah?
So what, sorry.
Go ahead, Sarah.
When you say it's time invariant, what are the sines and cosines of?
Of time. if you have a space from 0 to L and you have an arbitrary function in here, you can express it as a sum of sines and cosines. And if you shift this function, all it does is mix sines into cosines at the same frequency. So that's the sense in which it's translationally invariant. Like, I can translate this trivially in the representation without losing any precision.
But you're doing this for every different variable, not just time.
For now, let's imagine we only have time, but yes, we're
No, but
going to
if
do
you,
it.
I mean, it's an m-dimensional thing.
For now, let's imagine that these data points are ordered in time. This model is in time, and each of the columns of A is a time series. For now, we are going to go high dimensional. We are going to go high dimensional, but at first, let's imagine just one dimensional.
So essentially the W is for all the different frequencies, but how do you do the phase?
Well, once you have sine and cosine, you get all phases, right? You could
Oh, yes,
represent
you're right,
any
you're
phase
right,
as
you're
a
right.
sum of sine and cosine.
Yes. You're right.
Remember, those are the properties of sines and cosines.
Yeah,
Sines and
yeah,
cosines are the translationally invariant basis.
Yes, you're right.
Everyone, like, it's like, that's like, that is old school math physics, but, you know. So, sir, did that answer your question? That this, yeah, so it is the translationally invariant basis. Just the way that the spherical harmonics are the rotationally invariant basis on the sphere, sines and cosines are the translationally invariant basis on the line. So imagine you make sines and cosines, you make this sines and cosines. So instead of being m Kepler systematics, it's going to be m sines and cosines in here. Then this thing becomes as long as this prior has equal prior probability on the sines and the cosines at the same frequency. So the low power has some, and then the next k vector has a different prior and prior, and the prior only depends on k, and not on whether you're sine or cosine, then this becomes a translationally invariant prior on function space. And notice you can then produce any functions. Any function that can be made as sines and cosines, which is literally any function, can be generated by this prior. See? It becomes a prior over all of functions. Now, one issue with that, if you want it to really be a prior over all of functions, we're going to have to let m go to infinity. We're going to have the number of things go to infinity, and we're going to have lambda go to 0 in some way. So we're going to have the lambda values go to 0 as the basis gets infinitely large in some way, but it's provided you do that in a sensible way, this thing will remain finite. It will remain a finite n by n matrix. And so you can actually work in this infinite basis as long as you can somehow write this down without ever constructing the infinite matrices, right? And that's where the Hilbert space comes in. That's the property of Hilbert spaces. Hilbert spaces have the property that you can compute all the dot products between vectors with a finite function. It's called the kernel trick. So if you want to look it up, you want to look at this all up, there's the kernel trick, and it's literally called trick, and it's been applied all over the place. The most important places the kernel trick appears is Gaussian processes, which is what we're doing today. It's kernel PCA, which was the first nonlinear dimensionality reduction that was created. The first linear dimensionality reduction is PCA. Then kernel PCA takes the features up into an infinite dimensional space and then can handle nonlinear things. That's kernel PCA. And then there's kernel SVM. That's taking this linear classifier and making it high dimensional. So those are places the kernel trick is used in machine learning, but it's a very general thing. The kernel trick is that if you know the properties of this lambda vector, this lambda matrix, you can compute a kernel that computes the elements of this n by n thing without ever instantiating the whole thing. And we're about to talk about that. Good?
Can we go back 1 second?
Yeah.
So what you want to do, like your final goal for that piece is to make it what?
Ah, good. We haven't talked about why we're doing this. Damn it. Good. Good. Why are we going to do? Let's take a moment and talk about that before we go on here. Excellent question. Anna, keeping us attached to the real. Okay, so let's talk about in astronomy. How are they used? Here's one kind of use looks like this. I've taken some data. Here's X. Here's Y. This could be time. This could be brightness. And I have some data points. And I want to make a prediction for what happened here. Okay, and that's a problem that might be called interpolation, right? And you can interpolate these data, and the Gaussian process is going to provide a probabilistic interpolation of between the points. So what it will say is that your function, lives somewhere in this envelope between these points, and the Gaussian process can be used to make that prediction. Okay, that's one use. Yeah.
And that envelope is coming from the errors on your existing data points?
This envelope is partly from the errors on the data and partly from the properties of this prior. Because when you get far from any data, it has to use some prior information as well. So this width will be set partly by the errors on the data and partly by the width of our prior distribution over functions. I'm gonna give you an explicit formula for this in a minute. That's where we're headed. We're headed for an explicit formula for exactly how you would interpolate data, or what the interpolation formula is. It's really simple, it's beautiful.
I think a more sort of lowbrow way of
Yeah.
saying this,
Yeah.
correct me, is that when you think of formulating it, you would have discrete m's and you would have time bins and so on, because
Yeah.
really the data was discrete.
Yeah.
But it's often a fact in physics or mathematical physics that using Fourier integrals instead of having some concrete discretization is better.
Yeah.
And that's what you're taking advantage
Good.
of.
So I think it is true that one of the reasons that Gaussian processes are popular is they take a set of finite sampled data and produce a family of continuous functions that are consistent with those data. That's right, and that can be
And
used.
it's like taking a limit of a Fourier series.
It is, yeah, it is. It absolutely is. It is very much that.
Fourier sum, I mean.
Fourier sum, but with some priors on it to
Right.
control complexity, because we don't want the high frequency stuff to go
Right.
crazy. We're going to talk about how we control high frequency in a minute. But that's one kind of use. There's another kind of use of Gaussian processes, which is that you have some data like similar situation, and you believe that some of the variations in this data, some of the variations in the data are like shot noise, because the points are going up and down because you have individual measurement errors. Some of the variation is from the fact that the Kepler spacecraft is jittering, and some of the variation is coming from the fact that the star itself is varying. And we don't have a model for how stars vary. We just want them to vary continuously. So we're just trying to put a continuous model on this so that we can then see a transit, if it happens, on top of that continuous model. So that also relates very much to what Glennis just said. We want a continuous model that we can multiply our continuous transit model by and then compare to the data. So it's a way to put down a flexible, continuous model. But I could have done the same thing by modeling the data as a sum of sines and cosines, or I could have modeled the data as polynomials or whatever, or so I could have used a spline. Like a lot of times people are using Gaussian processes, it's just a way to have a flexible, smooth model that goes through the data. So that's what a lot of the uses are in astronomy. Yeah.
I mean, I look with Tyler Pritchett trying to understand Gaussian processes, and there's a very nice lecture by Jay Cunningham. I'm going to put it in the notes on YouTube.
Oh, please do, yeah. Oh yeah, I forgot to mention the notes. Do you have the notes open?
Well, just now. So, I mean, that helped me. I mean, there he sort of explains this, like you learn from saying like, I'm going to measure this I'm going to measure point Y at specific point X, and then I'm going to see how I can predict the next point and sort of
Exactly, yeah.
the point after or the point.
Yeah,
after.
we're about to get there. We're going to do that. We're about to predict new points. That's where we're headed. Yeah, and as I said in the so there's this notes, FCDA notes. That is where you can type notes if there are things you want to record. But also in the syllabus, I pointed you to. There's an online book, which is where most people learn Gaussian processes, this Rasmussen and Williams. It's a great book, but you will find it hard reading because it's definitely written from a machine learning point of view, not from a physicist's point of view. And one of the things that we've been talking about here at Flatiron is writing a replacement for the chapters 1, 2, and 4. The best chapters of that book from the point of view of us is chapters 1, 2, and 4, and it would be interesting to rewrite them from a physicist's perspective because the information there is important. Yeah, they're simultaneously easy to understand and hard to understand. Some of it's easy, some of it's very hard. We'll see as we go. Okay, good. Viviana, does that answer your question? What are we using this for?
Yes, I think yes. But I also was sort of like wondering about what kind of mathematical form do we want to put it in for this purpose? Like I just was wondering, you described the fact that you wanted to turn from, whatever base that system was into sines and cosine because that gives you translational invariance, and that basically says that this whole piece can be written as.
Good. We're about to rewrite that piece in a simpler form. Okay, good. Okay, good. So,
can I ask a
so
question?
now, if we're going to go what I call stationary, then indeed the limit that you take here has to be the limit that these are sines and cosines because that's the only stationary basis, the only infinite dimensional stationary basis. Although if you're on the sphere, it would be YLMs. Or whatever. If you're on different spaces, it would be different, but if you're on the line. Then it turns out that instead of writing A lambda A transpose, you can just write the elements, I can write the n prime element. This is a matrix that's n by n, and I can write any element of this as just a function, it turns out, of the difference between these two x values. So there's just going to be a function of the difference in the x positions that is the n prime element of this thing, even though this thing involved an infinite sum. So this involved an infinite dimensional sum, but that infinite dimensional sum can be replaced with this kernel calculation. And that is the kernel trick. And that is the defining property of a Hilbert space. So this is actually, shut up. That's literally, that's what I got from Wikipedia this morning. But anyway, of course, physicists think about Hilbert spaces because they come up in quantum mechanics. And a lot of the relationship here does relate to quantum mechanics because, of course, quantum mechanics is also a matrix theory. It's a linear algebra theory. So actually, there's a huge connection between the kernel trick and quantum mechanics. And indeed, the people who did these kernel tricks were all physicists. And a super interesting thing about machine learning is a lot of the most important things that have happened in machine learning have come from PhD physicists. A lot of machine learning comes from physics. And if you ask a lot of the machine learning people, they give a lot of credit to their physics background. Yeah?
Aren't these in the physics literature called Green's functions?
It's very similar to a Green's function, yeah. In some restricted case of the Green's function, this is the Green's function,
X is time, correct?
Right, in the example I'm talking about, X is time. So these are the time differences between 2 points. And this thing, first of all, it's called the kernel function. But if you're an old school cosmologist, this is also the correlation function. This is the autocorrelation function between the data. So in general, this function will have the property that nearby points have high covariance and distant points have low covariance. This is a measure of the covariance of the points. And at zero lag, this will give you the variance, and then at finite lag, it gives you the covariance. And what do these functions look like? Typically, x minus x, and whatever, xn prime, k, they'll look like this, or they'll look like this. Typically, there's really interesting ones. There's ones that look like this, that are like quasi-periodic. So there's ones that just have positive covariance. There are ones that are quasi-periodic that have positive and negative covariances because there's things oscillating. So if you have like an incoherent oscillator, whatever a stochastic oscillator would look like this, there are ones, it turns out the behavior of the function near zero is very important because small lags as high frequencies, so the high frequency power that you put in depends on this behavior here. And then if you want a more flexible model, like a more flexible model will be taller or narrower. You'll be more flexible because you're saying there's less covariance between the points. The function will be less smooth. And if you make it shorter or wider, you are making the function less flexible because you're allowing it to vary less and have the points be more coherent. So this is going to be, this kernel function that you're plotting, that you're choosing, is going to be choosing things about the flexibility of your model. If you let the kernel be very small, it allows the function to be very, very fast varying. And if it's very wide, the function has to be very smooth. And so it's actually a model complexity. It's going to come into this kernel. But in a beautiful sense that we can compute probabilities. We're going to be able to compute probabilities, so it's really, really nice.
So any of the components in your C needs to be functions from the Hilbert space because essentially you always try to do distances between model and data. Is that correct? Maybe not. You said like, oh, these are functions from Hilbert space and assume they're from Hilbert space because you need some, it's a distance. It defines a distance.
Yeah, yes, there is something about the fact that the Hilbert space has metric properties is somehow involved in here, but you are I'm not answering any questions about math.
No, I just looked Hilbert space up on Wikipedia. Why you mentioned Hilbert space?
The most relevant point about a Hilbert space is that dot products can be turned into function calls.
Okay. Oh, okay. Yeah.
These are infinite dimensional dot products.
Yes.
They become function calls. That's the relevant thing. That's the kernel trick. That, by the way, what is in common between GP's PCA and SVM, or what's in common between like linear fitting, which turned into GPs, PCA, which turned into kernel PCA, and SVM, which turned into kernel SVM? All three of these methods can be described only in terms of dot products of vectors. And if you only ever have to look at dot products of vectors, then you can go infinite dimensional, because in a Hilbert space, dot products of infinite dimensional vectors just become a function call. That's literally the sum of all math that I know. So I won't take any questions. No, I can only take clarifying questions about that fact. Yeah, hit me.
So the A lambda A transpose term, that's supposed to be like the gram matrix for this, but there's a lambda. What is the lambda in there?
Well, one way to think about it is lambda gets the units right.
Oh.
So you, good. So it's like a gram matrix, but the units would be, because A, remember, is a thing which you multiply by a weight to get data. I don't have it written down anywhere anymore. But A times the weights would be the data. And so if you did A transpose without anything in between, it would have units of data per weights.
Right.
So you have to multiply it by something that has units of weights squared to kill the per weights squared that you have and to get it into data units. So one way to think of it, I always think of things dimensional analysis. All my linear algebra is dimensional analysis. So dimensionally it has to be there.
Okay.
But it's also the case that it's a choice. So good. I think of this as a choice of a prior in the weight space, but it is equally well a choice of the metric in the weight space. You could have this be the identity. I could split this in half and put it into these two things, and then it would be the identity in here, and then that would be a choice of a metric in the weight space. And that connects very much to this Hilbert space, because this kernel thing has to do with the metric in the infinite dimensional space of the Hilbert space. So this is really a choice of a metric in that. Well, that's related to this whole thing that whenever you have probability, that's not metric, measure. I should say measure. Oh, is it metric? Oh, I'm totally confused. It's either measure or metric, but all of these probability expressions are about like measure and metric in some space.
Sorry,
Yeah.
can you hear
For
us?
the kernel function, there's no requirement that it's a function of the dot products between xn and xn prime.
No, in fact, no. in this context, the requirement is that it be a function of the magnitude of their difference.
Okay. So it just encodes distance between 2 points in some sense.
Yes, it's just distance between 2 points. And by the way, everything I've said here carries over for x being high dimensional. So this can be a vector difference between the 2 points. And in fact, we've done Gaussian processes. So if you're doing this as time, then your ambient, what they call the ambient dimension is 1, because you just have a time coordinate. But then if you're doing it in space, say you're doing Wiener filtering to figure out what the IGM is doing in space, K.G. Lee just wrote some papers like that, where they measure Lyman alpha forest clouds on certain lines of sight equations and then infer what the density is everywhere with a Wiener filter. There, the ambient space is 3-dimensional because you're doing a Wiener filter in the 3-dimensional space. And we've done up to 1,000 dimensions. We've done things where we made the systematics model in Kepler a Gaussian process of thousands of other things. So you can make this a very high dimensional space. In general, as you make this space very high dimensional, things get very hard to understand. So I don't actually think it's a good idea to go to high dimensions here, but it's a thing. And in the computer science literature, people work at very high dimensions inside here. You can, yes?
Is there any constraint for the kernel functions, like the integral has to be 1 or something?
There's a very strong constraint on the kernel function, and it's really weird. I'm about to state it.
Okay.
So hold that thought. Yeah.
I'm confused and maybe overthinking it, which is kind of a default state. But
Yes, that is usually your state.
So, but does this mean that the signal that you can extract from this has to be greater than the resolution with which your instrument is measuring the particular data that you're interested in? So saying the example of time.
Yes.
If you're examining something that has time signals that's less than whatever time interval your instrument is measuring, then you can't use this to like look for signals that are smaller than that. Does that make sense?
Yeah, I'm not going to answer that question exactly, but
Okay.
but it is still the case that if your data are like Nyquist limited, your
that's what I'm getting
inferences
at.
will also be Nyquist limited, which means that you're going to have choices about this kernel function, and you can put power at different frequencies in this kernel function, and there will be some frequencies where your likelihood function is insensitive to the power you put there. So there will be those same, all the Nyquist theorems carry over into this context.
Thanks.
Yeah.
But I mean, this function does not necessarily know about it. You can force it to make
You can
inference.
force it to make
But
an
it will be
inference,
wrong.
but it will be,
It will not-
it'll be
It
wrong.
will not
Jeff.
warn you.
Yeah, it will not warn you, exactly, very well said. It will not warn you that you've made a mistake.
It's like coding in C.
Yeah.
Yeah.
That violates the code of conduct, by the way.
Sorry.
At least the seed will segfault. This one will give you an answer.
Not my code.
The Zoom viewers are asking if you can turn the speaker on so they can ask questions. If
Yeah.
you don't know, they've also typed their question and I can repeat.
Yeah, get them to, there's people on Zoom.
Yeah.
Can they hear me? Can the people on Zoom hear me?
Yes.
Yes.
That's interesting, because I'm
Yeah.
not wearing a mic. I guess these things are good enough. The tennis ball,
That's
that's
the
the
worst
worst.
mistake.
Um,
That number comes
I
Have
had,
them,
I had their
them try-
question.
Yeah, hit me.
Can you repeat why lambda goes to 0 when n goes to infinity?
Why
It
does
isn't
lambda,
clear
good,
why the
I
metric
haven't,
would go to 0.
good, and I haven't talked about that. There's different ways of constructing these things here, and the way I think of it is going to a very dense set. If you go to a very dense set of sines and cosines, so you're getting very dense in K space to extremely high density, what you need to do is you need to conserve the power in a band pass. So as you increase the number of modes inside a frequency window, you need to reduce the power per mode so that the total power in the bandpass is the same. So that's the limit you're going to take here. But there's another limit you can take, which is you can actually stay on a fixed frequency grid, but take the grid out to infinity, and then this goes to 0 in the sense that the high frequencies go to 0. So it either has to go to 0 out in the tails, or it has to go to 0 locally everywhere, maintaining the power spectrum.
Is that the ultraviolet contestant?
Well, who knows whether that answered their question?
They'll respond.
Good. Feel free to interrupt me with questions from the internet. Good. Shall we talk about kernel function? Oh yeah, constraint on the kernel function. That leads into my next point. So it's true, you're not allowed to write down an arbitrary function there. The functions you're allowed to write down here have to be functions that are proper metric distances in a reproducing Hilbert space. Oh, so solve that problem. Okay, but there's a very simple condition they have to meet, which is mathematically intractable and also totally trivial. Let me say what it is. So mathematicians look at this conditional like you're hosed, you'll never figure anything out, and then there's a really simple way to always get it right. So the condition is that no matter that any matrix, where, oh, I should even say like symmetric. Any symmetric matrix made from K must be non-negative semi-definite. What's non-negative semi-definite? It's positive definite. But why am I saying non-negative semi-definite? Is technically you're allowed to have 0 eigenvalues. Okay, so it's positive, think of it as positive definite. These matrices that I've just erased have to be positive definite. A covariance matrix must be positive definite. Otherwise you can't take the log of the determinant, for instance. So any matrix you make must be positive definite, or technically non-negative semi-definite, but whatever. Think of this as positive definite. Now, if you just say to a mathematician, give me the space of all functions that have this property, they'll be like, that is like you get the Fields Medal for writing down the answer. But there's a really simple thing, which is that if you have a positive power spectrum, then you obey this if your power spectrum is positive, and the power spectrum is the Fourier transform of the kernel function. The kernel function is the covariance. Remember in cosmology, maybe not everyone here is a cosmologist, but who here has taken a cosmology class at some point in their life? Good, most of you. So if you've taken a cosmology class, there's the correlation function and there's the power spectrum, and they're the Fourier transforms of each other. If you have a positive power spectrum, then you meet this property.
So positive power spectrum means that on all scales positive?
Non-negative, I mean. If you have a non-negative power spectrum, then you meet the non-negative semi-definite.
Okay.
And the reason is sort of obvious. It's because think of the design matrix as being made up of sines and cosines. We need positive power on all this, or non-negative power on all those eigenvectors. So that's one way to think about it. So that means there's a very strong relationship between the kernel function and the power spectrum. And by the way, this is exactly how the Planck data analysis is done. The Planck CMB constraints are actually done by, they didn't make it, like you think of it as being power spectrum, you always see the CL plot with the wiggles, that's a power spectrum on the sky, but actually they're actually computing the likelihood of the data under the Gaussian process. I mean, they have to make some approximations, but that is what they're doing. And so you can think of the Planck data analysis as being a power spectrum of the CMB or the correlation function of the CMB. They're the same thing. Okay, good. And this double-sided arrow should be labeled Fourier transform, because that's what takes them back and forth with each other. Okay, good. So you have to have a non-negative power spectrum to be good. Okay, good. Now, good. I have said, okay, so that's all. Now I want to just say, I'm going to just state what the math is. Because we haven't done any math yet. Well, we've talked about a lot of math, but we haven't actually got the things down that people actually do when they're doing a Gaussian process. So let's write that math down, talk about why it has that form, and not prove it. Okay, so imagine I have these data here. So these values are collectively whatever my x values. These values collectively are my y values. So this is my x vector, this is my y vector, represented here. Now imagine that, I need a slightly longer piece of chalk. Now imagine that I want to know, at this x star, I have to do that occasionally just to prove that I still got it. Imagine I want to know at this x star, what do I expect here? So what we're going to do, and actually I'm thinking about one data point, but everything I write down is going to be for a vector of data points. So you could actually put down a fine grid here and ask, what do we expect everywhere on that fine grid? And that's in fact how people usually use the Gaussian processes. They're usually trying to make a smooth function through the data. So they're going to predict on a fine grid what is implied by these data points under this kernel function. So we've chosen a kernel function, and we're going to come back to how we choose it, possibly next time. But we are going to talk about how you choose your kernel function. And in that kernel function, I can now predict at any new points, including a grid of new points or whatever. I'm going to call all the new points I'm predicting at x star. And all the points I've already got x. And there's y, and I'm going to predict y star. See, that's the standard terminology in the business. And that's in that Rasmussen book. And here's the fundamental result. So what we're doing is we want to know the probability for y star of all the data at y, all the x star values, given the points at which I want those data, and given the data that I already have, which is the y and the x that I already have. And then, of course, there's the kernel function and maybe other things. There's various things you're assuming, but basically what we want to know is what is the distribution. And because it's a Gaussian, everything's Gaussian. The noise is Gaussian, the process is Gaussian, everything's Gaussian. This will be Gaussian. So this is going to be a Gaussian for y star, given some mean and some variance. Now, what is the mean and the variance? The mean is so incredibly surprising. The mean is something which I'm going to call k star, capital K star, times k, something I'm going to call k inverse times y. Actually, that is not quite right. C inverse times y. And let me just define these terms. K star is, or let me say, the n prime element of K star is the kernel matrix evaluated at xn and x star n prime. So this is a rectangular matrix that tells me what's the covariance between my old data and my new locations, my old locations and my new locations. I need to know the covariance between them. And this has to be rectangular because we're going from data that we've taken to new data that we want to predict, and they won't be the same dimension in general. So this is a rectangular matrix that talks about how we covariantly relate the data here to the data we are looking for. Yes?
The C minus C inverse there you written is the original data covariance, not
Good.
the 1 plus A.
It's C inverse, good. The C inverse is the original thing we had, the sigma n's UU transpose, plus our kernel matrix, okay, plus K, where K n prime is the kernel function evaluated at xn prime. So this is the covariance of the data, which includes both the kernel and the measurement noise, because the measurement noise is relevant to averaging the data. And then this is the thing which tells you how that covaries with the new data. And that is exactly a Wiener filter. That is a Wiener filter. If you can write down a noise model for your data, you inverse variance weight your data, and then you project it onto the new points using the expected covariances. So that is exactly a Wiener filter. Wiener filter, which is pretty cool. It took me a lot, I learned about Wiener filters a long time before I learned about Gaussian processes. So when I saw this, I was like, that looks really familiar. And there's all this cosmology literature about signal and noise, combining signal and noise into covariance matrices and inverse variance weighting things, and I finally, it all came together for me after I learned Gaussian processes. I never understood the Wiener filter when I learned it the first time. I was like, saw it, but I didn't know why it had this form. Why does it have that form? But the way I think about it is you're inverse variance weighting the data, and then you're producting it into the covariance structure to see what the new data are going to look like. And then there's also a variance. Actually, I should call this mu because I've overloaded m. So let me call that mu. And then the variance, what's the variance you expect? So the variance has an interesting property here, which is that if you get close to data you've already seen, the variance should get very small. And if you get far from data you've already seen, the variance should get very large, because it should return to basically the independent variance in the kernel function. So if you get far away from data, it should just basically go to this 0 level variance. And if you get close to the data, it should be constrained by the nearby data. So it has to have a strange property. So let's write that down. I'm going to write it down here. It looks like this. It's k star. I'm going to define yet another variable, k star star. You can guess what this is going to be. There's going to be k star star minus, and now, and minus is weird. And whenever somebody is writing it down a covariance function and writes a minus sign, you should be afraid, because covariances have to be non-negative semi-definite. And if you're subtracting, you can easily go negative. So whatever I write here better be provably safe, because I'm about to do a subtraction. That's bad. This is why you should not do the subtraction naively in your computer, because you will go negative. And people do all the time. Actually, you'll find if you just naively code up the things on the board, you will get negative. You'll get negative eigenvalues and things will fail. So you do have to think about it. K star K. Oops, sorry. C inverse K star transpose. What's this? This object is the kernel function where between the starred points. So this thing is the covariance matrix for the star points. Now, what is this? This is the covariance you would expect if you had no data. This is the prior covariance. This would be the covariance of the data of the points if you didn't know anything about the function in the space. So imagine if these are my data here, and I'm trying to predict points here, x star is all the way over here, what am I going to predict here? Exactly the prior of the Gaussian process. That's what I would predict. So that is this. And then the fact that we have data in the space lowers the variance of my prediction. The prediction gets lower because I have data in the space, and it gets lower in as much as it is covariant. Right, because this measures the covariance between the starred points, the new points, and the old. This is covariance between the new points and the old. This is the variance of the old. And so this thing says, is there covariance between the old points and the new? And if there is, it will reduce the variance. And then it's an exercise to the reader to prove that this thing never goes negative.
So in K star star is where you would put, if you had a detector where you put Mehmet's thing, where you would say, like, my detector, even if I haven't measured anything, my detector is sampled, you could put the Nyquist in the K star star.
Not going to answer that. I think what you said earlier is correct. You can transparently violate you can transparently do inference beyond the Nyquist limit, and whatever, you'll be. Because this literally, by the way, this K star star and this K star and the K that goes in here have to be the same kernel function. If they're in any way different functions, you've just messed up the math. And then this thing won't be negative, this won't be non-negative semi-definite, you're done.
Just a little quibble about the notation.
Yeah.
Maybe you would, on the right-hand side,
Yeah.
maybe you want to call it mu star and v star, because they know what x star was that you picked.
Good. Mu star, that's a very good notational change. Let's do that. I agree with that. They should have mu star and v star. Because yes, they know a lot. They know where the positions are, the new positions are, and they know where the old positions are and the old data, and they know the covariance structure between them. Exactly. So they really, that star indicates that it's the future, not the past. Yeah.
So the C is the thing you learn, and computing the kernel is the work you do every time to predict stuff.
Good. What are the things you need to do here? I don't know exactly what you're asking, but every time you change the kernel or change your data, what do you have to recompute? You have to reconstruct the C matrix. You have to either factorize or solve the C matrix to do this operation, and then you have to do this dot product, and you have to add it to that. We'll subtract it from that. So you do, every time the data points change, you have to recompute whatever you need to recompute here and go. But the calculational cost or whatever is usually in this operation. That's where you spend your money. Because this is just function calls to your kernel function, but this you have an n to the 2.6 inversion or solve or factorization here to do that operation. I don't know if that's what you're asking.
Yeah.
Okay, good. We're going to talk about something that's even slightly harder. Are we? Oh no, I still have a few minutes. Yes?
Where do you input your dependence on the error? Because you'd think you'd have a lot higher variance, even if you're really close to another point, if you have a large error bar on it.
Good. The errors are in C,
Okay.
see? So these are the individual point error bars are still there. We haven't forgotten about them. By the way, in the Gaussian process literature, people often drop this term and they work in the no noise limit, like the limit that you have noiseless data, which is, first of all, extremely numerically unstable to work in that limit. And second of all, it is totally unrelated to anything we ever do. So for us, we always need this term here, and that term is in here. And by the way, how does that appear? You just said, if your noise was large, then it wouldn't be very constraining. Let's just check. So if we make the noise very large, sorry, this shouldn't be C inverse, that's C. If I make the noise very large, C becomes large. Then I take the inverse of C becomes very small. And then even if I'm very covariant with those data points, even if these data points are very covariant with those, they still get zeroed out by this C inverse. And so they don't actually subtract off much variance. And then dimensionally, you can see that this is correct because this has units of variance, variance, inverse variance. So this is a variance tensor, and this is a variance tensor, so it adds to a variance tensor. So there's like, dimensionally it holds up, and it also has the nice scaling. Does that make sense? Is that good? But good. In fact, when I first wrote this down, I was actually having that same thought. I was like, uh-oh, can't I violate the non-negativity thing here by just making my errors large? But no, it's just the opposite. When your errors get large, this object gets small because it becomes and that was a mistake. That was good to catch that mistake.
And if you're trying to do this on one of your, let's say, old points,
yep,
then basically K star becomes K star. Like I would imagine that there you would just want to find C.
Yeah, good.
Something like that.
Okay, imagine you're trying to predict. Good, you're asking a nice question. What if you're trying to predict right back on top of one of your data points? So then the interesting thing is, if there was no noise, see if there was no noise, this would be K inverse K, and you'd be taking off of K. And so you would get exactly 0 here. You would exactly predict that its value should be its value, which is a pretty good prediction. But then as the noise grows, this term gets smaller than these, and then this doesn't take off all the variance. So imagine you're just predicting right back on the same points. So this becomes K, this is K, that's K, and this is a little bit smaller than inverse K. And so this whole thing is a little bit smaller than K, and then it's smaller than that, and therefore it doesn't take off all the variance, and you get a little bit of residual.
Right, you get a bit of residual, and I thought that the residual should be exactly the error, like the sigma.
That is. Oh no, I think it is. I think it is.
But not quite.
No, I think
right?
it is because
Unless
okay. So this is of the form A plus B inverse A. That form has interesting properties. If you play with that form, you might find that you do get the error out, but it's an interesting question. You can manipulate that. If you play around with your matrix identities, you can manipulate that. Yeah, these forms appear a lot in data analysis, by the way. That is a very common form in data analysis. It appears all the time. So being able to manipulate expressions like that is super valuable. And sometimes there's crazy simplifications when you do big problems like this. But it's always worth thinking about linear algebra, not just using the canned packages. There are canned packages for everything here, but it's worth thinking about linear algebra before you turn on the canned package, because sometimes you have tricks. And we're gonna, next class we'll talk more about like how we actually implement, but I want to say one last thing before we go, which is the following. Yeah, I'm gonna erase, although I should probably never erase the example. The reason we're doing it is probably not the thing that should ever be erased. But anyway, remember we started by saying that the log of the probability of my data given my model and various things was -1/2 y minus m transpose C inverse y minus m. Yeah, that's correct. Transpose, yeah. -1/2 ln. There's a 2 pi. Okay, I said that earlier. Now, remember that inside this C is something plus K. The kernel matrix is inside here. That means this thing puts a probability on the kernel matrix, or puts a likelihood on the kernel matrix. Because this is the probability of the data given the model and the kernel matrix, and maybe some other things. So this is actually a marginalized likelihood for the kernel. And some people may recall that I've said you should never compute a marginalized likelihood ever. You're always making a mistake. And that's true, but in the case of the Gaussian problem, you have a closed form for the marginalized likelihood. There it is. It's the marginalized likelihood. That means you can do inference on the kernel in two senses. One sense is, if I have a parameterized kernel, I can learn the parameters. I can either do maximum likelihood for the parameters, that would be the empirical Bayes, or the maximum likelihood, or whatever the Fisher optimal estimate for the kernel parameters would be to maximize this likelihood. And then, or you can do Bayesian inference. You can put a prior on the kernel parameters. Maybe you know some things about the power spectrum of the thing you're looking for, or know rough things. And you can put a prior on the power spectrum. That puts a prior on the kernel parameters. And then you can do Bayesian inference with this as the likelihood. There's your likelihood. And then thirdly, if you have two qualitatively different kernels, so one thing that like Daniela Huppenkuthen and I work on is there's a flare from the sun. Is it showing quasi-periodic oscillations? We can compare a kernel that has oscillation structure to a kernel that doesn't, and we can compare them with a likelihood ratio. So we can literally get a likelihood ratio, or even more horrifying, a marginalized likelihood ratio for the different models. Or you can put in a utility and compute your expected utility over outcomes. I mean, you can do anything that a Bayesian can do on the kernel. So unlike most model complexity, there's model complexity issues here because you can set things about your kernel. But unlike almost all of those situations, you actually have a really well-defined likelihood for the models that have different complexity here. And so that is a very interesting aspect of Gaussian processes, and it's one of the reasons why, I think it's one of the reasons why astronomers are drawn to them, because most of the times we face model complexity issues, we have nothing to stand on with respect to model complexity. We have to go to cross-validation or something. But here you have a very kind of principled, well-defined way of thinking about model complexity. And that area of inferring the kernel in the literature is called kernel learning. Called kernel learning, where you figure out your kernel, and there's some really beautiful work in kernel learning where people actually go all the way to the power spectrum and find non-trivial power spectra that do a good job, and they can do things like take a photo of Andy's shirt and continue the pattern out into the people who can't see it on the video. Andy's wearing plaid, which has a very non-trivial covariance structure, but you can learn the covariance structure of like complex patterns and scenes and stuff. So there's a really beautiful literature here. And some people in astronomy are starting to do kernel learning. They don't call it kernel learning, but they are working on the Kepler data, and they're actually computing posteriors over kernel parameters for stellar variability. That's kernel learning. And that's a kind of exciting new area for astronomy.
It sounds like there's one application you didn't mention, which is, so the assumption of stationarity wouldn't be a good assumption in spacecraft
That's right.
necessarily. But it seems like there would be a pretty straightforward generalization.
There
where
is.
you-
There is. Let me just, Glennis just gave me the opportunity to say, what is the model we actually used? The model we actually used in K2, when we were doing our K2 planet search, this was with Foreman Mackey. Our actual model, our noise model, so when you're searching for very weak signals in data, it's all about your noise model, and it's all about being very careful with your noise model. And our noise model was, so this is like Foreman Mackey et al. And I don't know what year that would be, 2015-ish, 2016? Yeah. Anyway, there's various papers. There's also, I had a student, Dong Wang, who also did stuff along these lines. And the covariance matrix, our model of the covariance matrix was, as usual, the diagonal noise thing, because we do believe the points have independent photon noise, plus a Kepler systematics model, which was A lambda A transpose, plus a kernel. And for this we used a rigid systematics model, which we learned from from other stars, but we constrained to be only the spacecraft as much as we could. And this was a generic like Matern kernel or something, one of the generic Gaussian process kernels that produces smooth variability. This was the photon noise as reported by the Kepler spacecraft. And because we treated each of these as an additive component, they just, the variances just add. And so it's completely generalizable, exactly as you say. And in fact, you can keep on going. You can do multiple kernels. You might have different noise sources with different power spectra, and you could just add them on too. You can just keep on going, and you can add non-stationary components and stationary components, and yeah, it just keeps on going. And you can make things depend on more and more variables. Like you can have a kernel function here that depends on time differences, but then we could have put in a kernel function that depends on temperature differences, and another kernel function that depends on spacecraft pointing differences. So we could have like, there's so many, that's one of the reasons why people love these models, is they are compose, as it were. They're composable into much more complicated models. And since you can compute in closed form your likelihood under those choices, you can even make like principled choices among the options. Okay, good. Let's close there, and then next time we'll talk about like how you actually do this in practice. There's some issues and there's some choices you can make that make things tractable and fast and safe.